So this video is for question 3 in the Acousto Optic Modulator lab. There are some settings that are mentioned in your lab manual for this lab. Right here it describes the generator settings, and in particular there's a 400 kilohertz square wave that's being asked for. And if you'll recall, that 400 kilohertz square wave, that square wave is causing this radio frequency generator to output bursts of radio frequency electromagnetic waves. And on the oscilloscope, the upper channel, channel 1, this picture up top, this trace is the trace that's following. It's a picture of what the generator is outputting. So during this time here is when the radio frequency waves are coming out, and then during the time after, there is no radio frequency waves. This picture right here is a picture of laser light coming from the laser here, bouncing off this mirror, going through the Acousto Optic Modulator crystal. If you look real careful, you can see the laser dot going into the crystal is on this side. It's on the left side, or the lower side. Travels through the lower side and is periodically being split into multiple beams because of the radio frequency bursts. And what that looks like is you can see these multiple dots. If I turn off the power, to the radio frequency generator, then it no longer makes all of those dots, right? The laser just goes through it as if it's a piece of glass. But with the waves traveling through periodically, we get to have these other dots. The dot that we're going to allow into the photodiode is the dot that's here. It's the third one over, right? There's one really faint one, a big bright one, that's the original dot, and then another bright one, which is a Bragg reflection dot associated with m equals to 1, and then there's even a fourth one over there that's dim. But you can see it's that second one we're going to keep and allow it to get tracked inside of the photodiode. So you can see that there is a dot inside of the photodiode eyeball, and there's a really bright dot that's the original laser beam dot, right? If I turn off you can see that the other dots go away, right? So what's being tracked in the photodiode is that second dot that only shows up because of the waves in the crystal, and this is the trace of it. And you can see that if I block the light over here, you can see on the trace, right? This is me blocking the light. It's really hard to do this. Yeah, you can see it. Okay. So what we're going to do is, so the laser is traveling through the near side, right? You can see the dot, and this is a diagram of it. So this is the crystal, the gray box, and the laser is traveling through the near side, and the initial position of this crystal we'll say is at 8 millimeters, 8.00 millimeters, and that is what you'll see right here on the micrometer, the location of this little crystal. And the idea is if we use this micrometer to move the crystal towards you, right, down, then the laser will, instead of passing through the near side, it'll pass further up inside of the crystal, looking more like this picture, right? So I'm going to translate it from 8 millimeters, that's the starting position over there. I'm going to move it over by 4.00 millimeters to a new position of 4.00 millimeters. And then I'll show you how the time gets measured. So this is what it looks like to translate the crystal. So I want it to move this way, so I need to tighten the screw in that direction. So this is tightening the screw. And if you look real carefully, you can see the crystal drifting while the laser beam stays in the same place. And while that's happening, you can see that, can you see the trace is moving, it's drifting over towards the right? So let me make sure that this thing ends up at the 4 millimeter mark. So right now that is, nope, that's not the 4 millimeter mark. So this position is the 5 millimeter mark. You can just make out the 5. And then this is the 4.5. And this is the 4 millimeter mark. And here is the new location of the wave. So very carefully, this was actually the original position of the, here, I'm going to show you again. So I'll just back this out. Oh, sorry. I should have rehearsed this. So this goes out to the 8. Is that the 8? Nope, that's the 7.5. So the 8 is here. I'll just place this cursor at the beginning. That's the beginning right there, right? And you can see that, right, the signal is there. What I'm trying to mark is this location here. And when I move the cursor back and forth around that, you see a fluctuation in the time up here, maybe of like 20 or 30 nanoseconds, right? So there's like an uncertainty in just where to place the cursor. And now I'm going to drift this crystal over to the 4 millimeter mark. So I got to rotate this direction. So coming up on 5, there's the 5, the 4.5 again, and the 4. Okay, so I didn't move this cursor. I'm going to leave it there, but I'm going to move this cursor to mark the location of when the light shows up. So that is around like in there somewhere, right? So this time span here is the extra time because of the extra distance, right? So because we move the crystal from here to there, waves in the crystal that start on the bottom side, right? Actually, let me draw them in gray. These are waves, acoustic waves, that travel across the crystal at the speed of waves in the crystal, right? So they travel across. Over here, they didn't have to travel very far before they can split the beam. But here they have to travel quite a bit further. They have to travel actually 4 millimeters further. And this right here is the amount of time extra because of the extra distance there, right? So from this information, you can get what's called the group velocity.